We're here today to tell you a little bit about our experience adapting our expertise in mechanical and electrical inspection of movable structures to address those of the NTIS and complex tunnels. So if you were paying attention during that last presentation, you now know what this is. If you haven't been through the FHWA, so I'm not going to go ahead and talk about it. The only thing I really wanted to mention is how intermingled the mechanical and electrical elements are, because it is a struggle for us to identify how to convert our rating system in order to report to the FHWA. So this is a map showing most of Western Washington, and each flag on it is a tunnel that has fire or electrical and mechanical elements that we need to inspect. 7 structures are major tunnels that are complex and are massive. And 3 of those are actually the same tunnel that's been added onto a few times. So for reporting processes, it's separated out.
The next few slides, I'm going to show you some examples of some of the tunnels we inspect. This first one up here is one of our most complex tunnel systems we look at. It has extensive mechanical and electrical systems. Next one up just has ventilation and lights. This one has lights, pumps, and fire hydrant connections. This one just has lights, and this one we just structurally inspect, not ourselves, but other people in our group. We have nothing to do with it.
So what you see on the screen is a screen print of our reporting software. It's Bridgeworks. It was developed in-house and has been used for a number of years for reporting on our state inventory. We've began to use it to report on our tunnels, and we have tunnel-specific elements that are different than those presented in the SNIDI. So I'm trying to figure out a way to convert that, which is fun. And then you read through it a little bit, and you'll see that we point out things like all inspections aren't equal. You know, deficiencies located in the roadway were left over from previous inspections because the roadway was not accessible during this routine. So here is a routine inspection report that we generate. It will have every component of that system with an associated note documenting its condition, as well as who inspected it, the hours it took, what the tunnel was, and your ratings. And then here's a cover of an in-depth report. So our routines are done every 2 years. Our in-depths are done every 6 years. And the in-depths are a massive undertaking. They take weeks. And with multiple teams of mechanical, electrical engineers to go through some of our larger structures. And the reports you get out of them are literally textbook size, and they're discipline specific. So it's a big deal, but they're very useful in identifying issues, and you do special testing during them. So if you're going to have a safe and successful inspection, you kind of got to take Abe Lincoln into account. He once said that if you gave him 6 hours to cut down a tree, he'd spend the first 5 sharpening his axe. It's the same approach when you come to inspect. You got to look and know what the hell you're going to look at and how it works and what order you're going to be doing it in. So you review these documents, and the operation inspection and maintenance manual is something that's kind of unique to us. And really, they don't exist for our tunnels yet. They're in development. They're a concept we have in application on our movable structures, and they're the equivalent of your Honda's owner's manual. So anybody showing up to the bridge that wasn't trained in expertise on the bridge could run through procedures in order to operate. You know, if you were on a movable bridge, how to raise or lower it, or if you're in a tunnel, how to initiate a dump or back out of a dump that may not be necessary. So every morning of the inspection starts with a pre-activity safety plan. It's essentially like what are you doing, where are you going to be, what are the hazards, what PPE do we need, and when do we expect you back. So it's getting everybody on the same page so you come home safe.
So pre-activity safety plans are reviewed and signed by all involved personnel, and they list hazards that might be encountered during that day's work. Also, there's some other precautions you have to take into account that aren't immediately obvious. One example is we practice the lockout tagout procedure. When you're working on a fan, you can lock it out and tag it out, but that doesn't exactly mean that's going to prevent it from moving, especially on intake fans. Airflow generated by other fans that may be on during your inspection can spin up that fan that's been locked out and tagged out. And if you're inside that fan, taking a look at some of the blades, that can be a problem. Also, some of our tunnels have traffic loops inside of them. These loops are there to mitigate any CO buildup from vehicular traffic. During inspections, if you have an inspection vehicle parked over that traffic loop, it may turn on that fan unexpectedly, so you have to be aware of that as well.
So depending on what you're working on, you really need to know the hazards associated with it. The men in this picture are donning arc flash suits because they're working on an energized medium voltage bus, and the danger of an arc flash is very real. If you don't know what it is, it's essentially a electrical fault igniting plasma through the air, and it's like a big lightning strike in front of your face. So be aware of what you're doing, come home safe. This is the actual typical PPE everybody on a tunnel inspection usually carries. You know, it's your basic stuff. You probably have it on any one of your movable bridge or normal bridge inspections.
So communication is key to have successful inspection. We always designate a single point of contact. This person will take all communication from each of the inspection teams and also coordinate where each team is going to be during that day's activities. Some of our typical communication devices we use are radios and cell phones. Unfortunately, these don't work well in large concrete structures. There's basically no service on radios or cell phones. A lot of our tunnels have hardwire phones we use to communicate back to that single point of contact.
So if you're ever planning a tunnel inspection, the ideal is while the tunnel's closed. But that's not always the reality, because most of the time you're in some downtown and you wind up getting a lane or two. So make sure you're aware of who your traffic control people are and that they know what your plan is, because it's a lot better if they hit the pillow than you. So
situational awareness, also key to our inspections. You have to be aware of the traveling public, even if the tunnel is closed. You also be aware of your surroundings and other authorized people that shouldn't be in there. What you see here on this slide, this is one of the entrances to one of our tunnels, the Bremerton Ferry Tunnel. The ferry offloads every hour to hour and a half. Within that hour and an hour and a half, the tunnel can seem like it's closed to traffic, but it's still open. You may only see a few vehicles within that hour and a half, but you need to be aware that it is still live. Brings us to tools. Up on the slide, we have a vendor performing vibration analysis on one of our centrifugal exhaust fans. Some of my inspection tools that I use most frequently are just a flashlight, my camera, a mirror, telescoping mirror, and a 6-inch scale. These 4 tools are used more than any other. Some of my more in-depth tools are an infrared gun. Even better, an infrared gun I found to be an infrared camera. It gives you an image of what you're looking at. And also a tachometer for measuring RPMs on motors and tracking that through time. This is an example of one of the images from our infrared camera. Up here is an image of a hot fire pump bearing. This bearing was running about 20 to 30 degrees higher than the adjacent bearings that were running on a similar system. Also, access is key. A lot of our tunnels have dedicated man lifts, and if not, we bring them in to get access to equipment that is hard to reach.
So to access about 95% of electrical panels, all you're really going to need is an 11-in-1, a small crescent, and a channel locks. But this is everything that comes with me wherever I go. And then there are specialty cases where you're going to need other equipment. And then here's the more fun aspect of what I do. And the meters outlined here, the Megger, is an insulation resistance meter. And you use it in order to get a history of conductor health, essentially, so that you're checking its insulation resistance phase to phase and phase to ground. And it's time consuming, but it's really helpful if you do it over a period of time. You can see when things are degrading and when to replace them. And then this right here, the ground resistance clamp on, is very nice to have because it directly tells you what your resistance to your ground electrode is. and you can verify that you actually have a safe path to ground so you can carry unwanted electrical current off of equipment and away from people. And then these are awesome too, with fluke clamp-ons. They're inductive ammeters, essentially. You can measure, you clamp them on, and then they also have a flexible CT that comes with it, so you can get motor operating data and build a history, and it's very nice concerning the new NFPA 70E, which is electrical safety in the workplace, because you can put that long leash and walk back and not be standing in front of an open panel, so you have to change your PPE requirements. And then also infrared cameras are invaluable, and I'll show you later.
So bringing us to operational testing. On movable bridges, we always operational test each of the systems. Unfortunately, in the tunnels, it is not as easy to do, especially with a deluge system. A lot of our tunnels use a foam deluge system. To do an operational test on that, you'd have to close the tunnel, and then you'd have to deal with the cleanup and the cost of the AFFF foam that you just released into the tunnel. So it's not real popular to do. So you have to operate where you can and when you can. One of our operational testing is a standpipe operation. Here I'm testing a standpipe for proper flow and pressure. Make sure you wear your raincoats. Also, we use that operation to test our sump pump pits and float switches to make sure their operation are working as they should as well. During this test, we also accidentally operated the hydrocarbon sensor that's used to detect explosive gases. Make sure you don't operate a pump when you've got explosive gases. We flooded it out, so we had to acknowledge that alarm before we continue our operation. So this brings us to some of our tunnel inspection findings. Up first is our most complex tunnel complexes. This is the Mount Baker Ridge and First Hill Lid in Seattle on I-90. So up here on this slide is an exhaust fan bearing. This fairing is packed with grease. You can see in the slide there's kind of a puddle of oil down below. It's not exactly deterioration, it's just the oil separating from the thickener in the grease. These bearings are repacked on a set maintenance schedule. So I wasn't too concerned when I saw this. But on the next slide, we have kind of a similar thing happening, but this is on an exhaust fan damper operator. This exhaust fan damper operator hadn't been repacked since installation in the late 80s. Oil's leaking out of it, so at some point it's going to need to be cleaned out and serviced. Up next is an emergency egress route. As you can see, there's a few tripping hazards along your way to safety, especially some irrigation nozzles that are kind of popping out of the ground in inopportune moments. Here we have a retention tank. These are located outside our tunnels. These are meant to trap effluent from the tunnels in case there's a spill or a foam system dump. I guess we have we're operational and testing these during our first in-depth inspection. They work just fine. Unfortunately, these are all manually operated, so in the event if you actually had a fire or foam dump, personnel would have to travel out to these retention tanks and manually close them to keep the effluent from running into Lake Washington. Not really feasible in an emergency situation. Also, there are no parking restrictions located over these, so you could go out there and you couldn't even operate it anyways.
So during testing in that tunnel, VFDs are used to run the centrifugal fans, and they're ancient by our standards. So if a dog ages 7 years in a year, electronics really ages 20 years in a year. So a lot of our equipment is like straight out of the 80s, and you design tunnels to last 75 years, but the electrical equipment really isn't going to do that because it isn't going to be supported over that time. So these VFDs are a clean example of that, in which they had multiple parts fail during the inspection, and it's incredibly hard for them to find new replacement parts for it. And they were also put in place during older codes where clearance has changed now. Now you can't have a grounded device within 42 inches of a live bus and your 38-inch separation there. So to address this in the light rail expansion, those drives are now actually out near the centrifugal fan motors, and they've been replaced with modern equivalents. And then here's an example of testing that we do during our in-depth inspections of those structures. And it's a real specialty case thing because it's time-consuming and expensive. You have to rack out each medium voltage circuit breaker and hook it up to a load bank in order to make sure that it actually operates as it should. Because it's a protective device, you want to make sure that it opens under the conditions that you set it to. And they did find several interlocks that were bent or broken, and then status flags that are indicating the wrong thing. So, I mean, it takes a long time considering you have about 80 medium voltage circuit breakers there, and you got to take each one out of the rack and test it individually and then reinstall it. So here's a much more typical finding. In tunnels, you have tunnel lighting contactors, usually that control one or more lights. Usually it's a bank of lights. But these are usually closed for long periods of time, meaning that electrical current will be running through the contacts. And as that happens, you wind up getting pitting, which will increase resistance and potentially cause a fire hazard over time or cause power to not flow through. So it's just a more typical thing to check on when you're looking through and you have, say, 50 tunnel lighting contactors, like in this tunnel. We open these up and look and document condition randomly. And then during in-depths on each one. And then obviously you don't want Jumanji going on inside your load. So yeah, this is a medium voltage. I think it's 14.8 kV, and they have all sorts of plant matter growing up in it. This was before I was actually with WashDOT. But during this inspection, they had the PUD come in and kill power and clean this out. And it's a potentially huge fire hazard.
So this brings us to our newest tunnel, the Bremerton Ferry Tunnel. Primarily serves offloading ferry traffic. It is our newest one to date. I guess we have a new viaduct tunnel coming soon. So on our first inspection, we found that some of the access inspection covers on the fans were missing hardware. We don't want to leave it like this, as it could possibly vibrate loose over time and fall into live traffic. So during our inspection, we brought in maintenance crews and drilled and tapped for new hardware to secure those access hatches. You can never have enough photos when you do an inspection, even if you're not finding a deterioration of any sort. They're invaluable for future inspections. So this photo was taken during our first inspection. This is of a exhaust manifold on one of our generators. The subsequent inspection, we found one of the bolts holding that exhaust manifold on was broken. So we noted it and had maintenance come in and fix it.
So what you're looking at here is actually the enclosure that houses the programmable logic controller for that tunnel. So I'm going to refer to it as a PLC going forward. What a PLC is essentially the brain of the tunnel. It controls the logic for how devices operate, what state they should be in given different inputs. And most of these systems have backups where you won't just have one PLC, you'll have like PLC A and PLC B. So that in the event one fails, you can switch to the other and you're not out of luck. We got here and there was a do not operate tag on that switch because there was no program in the A processor. When they were doing the first startup of this tunnel, they had not set that PLC to boot from non-volatile memory, and they had also not loaded non-volatile memory, meaning that the second power was lost in that PLC, you no longer had a program in the PLC and it would do nothing for you. So it was operating on B, we reloaded it and corrected that. But a potentially bigger issue, which is the giant red arrow pointing at the bottom, if you open this cabinet up, you'll see a ton of conductors in there that are all, and the thing boxed there is the PLC I'm actually talking about. But this entire cabinet was not anchored to the ground, so if you did have an earthquake that caused it to tip, you're probably going to shear most of those conductors and be in a huge problem. So another issue with this inspection was that there's no documentation for functional testing of the control system ever having been done prior to us accepting it. So we actually brought in Panatrol, which was the company that did that coding, and we ran through their functional test document and corrected a few things, and then added a few things and corrected some timers to reduce nuisance callouts. So I mean, it's always good to look for that, and to actually test it and make sure someone has. This is something I was kind of nerding out about when I got there. It's an armored cable that's fire rated to last for 2 hours. And what you're seeing is the effects of leaks that have been there since day one of us having the tunnel. And it's just a green patina and corrosion over it, but you know, obviously you don't want your armored cable corroding, and it's something to monitor. And as was mentioned in the presentation before us, maintenance personnel are like a huge resource to you. I can't stress it enough. Because especially with lights, not all lights are supposed to be on at the same time. Most tunnels have step lighting where it'll match the light inside the tunnel based off of a photoelectric sensor outside, so that you're not driving into an overlit or underlit tunnel, and it'll change throughout the tunnel. And something to note about this is when talking to maintenance personnel, one of their big gripes was their 400-watt fixtures. To date at this inspection, which was only 4 years after the tunnel had been opened, 40% of these had failed and they'd been rebuilt. And it's not something I would have known having just gone through. So this is a specialty testing that we did during that, and you're looking at light levels in the tunnel as the traveling public sees it, and then also as was reflected off of the walls in the tunnel, so that you can assess whether or not you're meeting the lighting standards necessary. Because if a tunnel is overlit, you may be driving into a black hole as a traveling public, because your eye doesn't adjust as fast.
Brings us to our next tunnel. This is the Washington State Convention Center. It's located in Seattle, Washington. It's technically known as an air ride structure since the Washington State Convention Center is located over it, and it opened in, I believe, 1988. So the mechanical findings we found, up on this slide is a foam pump for the fire suppression system. It comprises of couplings, a gearbox, and a pump. One of the couplings is known as a grid coupling. After opening it up, we'd found it hadn't been greased since installation, and since 1988. Luckily, it's lightly loaded and it isn't operated very often, so there wasn't really any appreciable wear, but during the inspection we did grease it up as it's supposed to be done. Up next, this is a missing section for one of the fire suppression piping inside the tunnel. This would cause a severe problem if there ever was a foam operation in this zone, as there'd be a large pressure drop from this missing section. I believe it was taken out by a high load hit inside the tunnel, so it kind of tells you something. Also, this is a ventilation fan, just serves a electrical room. This kind of illustrates that communication is key in maintenance. This was you can see here the fan belt is severely cracked in a few different spots. This illustrates there needs to be communication because none of the maintenance, there's different maintenance groups for this convention center and tunnel, and none of them thought it was their responsibility to take care of this thing, so it just kind of lapsed. Here's a deluge valve. This controls water flow to the zone valves of the fire suppression system. During the inspection, it was found that a downstream valve was leaking with a steady flow. This kind of illustrates that the deluge valve has a leak in it and will need to be serviced sometime in the future. Right now, we're just monitoring the flow to make sure it's not getting appreciably worse.
So earlier I mentioned that IR cameras are very useful for electrical findings. Specifically, they're extremely helpful in finding loose connections. Phase A on this contactor had been replaced in an earlier inspection because it had wear spots on it and we had extra conductors and we might as well have just fixed it there. Turns out we didn't torque it down all the way. When I came back for the next routine, it was significantly hotter, and when I pulled the cover of that lighting contactor, it was pretty burned up inside, and so we wound up having to go through there. And that's an extremely useful tool. So this is a not so new PLC, and by not so new I mean latest and greatest of the early 80s, so it's about 600 years old if you use that adjustment I was talking about earlier. And it had all sorts of issues when we showed up. The spare PLC had no program in it, and at the time the loader that they would use to load that was about the size of a desk and used tapes. We wound up using one of our loaders in order to reload it. But a bigger issue was that the control power for rack A was tapped off of the load side of a GFCI inside there, which means if that ground fault interrupter popped, there goes all the power to your PLC and you had no programming. When we went to their emergency bus, which is the thing in the background, you see foam pump 5, foam pump 6. Neither one of those is our foam pump. Our foam pumps are actually the unlabeled black breaker down to the right. And then finding the utility breaker for that was interesting because talking to our personnel, they had no idea because it was a convention center device. And then talking to the convention center device, they had no idea where it was. Turns out it's in a small closet-sized room across the entire convention center. So that's an interesting exercise right there. And well, the main thing there was we didn't want to start their 3 massive generators because they have conventions ongoing and they're very loud. So we were trying to do everything we could to isolate that and then lock those out before we began breaking or killing breakers. Here's a finding in the tunnel closed sign. You can't really tell because the ivy's eating it. And then you go downstream and there's more tunnel closed signs and the wonderful people in Seattle have tagged them and decorated them in their own way.
So this brings us to the last tunnel of the day, the Battery Street Tunnel. This is our oldest tunnel we have looked at. It will be replaced by a new viaduct tunnel. And it has a lot of original equipment, and a lot of it has been Band-Aid fixed in anticipation of this new viaduct tunnel, so I'm happy that it broke through today. So some of the mechanical findings, it has just a straight water deluge system. This system is old, and it is a Rube Goldberg. It uses an air line that runs throughout the tunnel, and if there ever is a fire, that fire will heat up that air line and drop a weight, which will in turn open up a deluge valve. It sometimes works. This is an internal view of one of the deluge valves. During testing, 3 of the 14 deluge valves failed to operate when tested. Not very confidence-inspiring. Here's an air compressor used to maintain air pressure in that air line. The air line also has a valve that adjusts for ambient air pressure and temperature. Make sure you don't accidentally dump water into the tunnel, which I guess has happened quite a bit according to the maintenance personnel. So I'm sure the traveling public will be happy once they get out of this thing. Here's one of the detectors inside the tunnel. It's just a large metal disc. Just has a lot of surface area for the heat to heat up, I guess. And it brings us to electrical.
So what you're looking at is a temporary installation of a camera in the tunnel. And you don't want PVC in tunnels because when PVC burns, it emits noxious gas. So that's just what I'm trying to point out there, because if you're a civil person walking through a tunnel, it would be easy for you to see. And then here is in one of the roadway foam pits. That tunnel is 100% a Band-Aid right now. And what you're seeing here is a replacement power feed because the original had failed. And as an electrical inspector, it's not what I like to see, in that conductors run outside of a raceway in a wet environment with connections. It's really not, doesn't make me comfortable. And then this is a limit switch that monitors whether or not you have one of the deluge valves racked in or out. And the base was cracked, so that the little bump that's on that rod as you spin it, that's supposed to actuate that limit switch, all it did was cause the limit switch to bump up and down and never give you an electrical signal that you had that locked out back in their control house. So that could be a problem. And then here is another latest and greatest of the 80s. But this was originally why we were actually asked to come back and look at this. It's because they had no program in it, and this PLC is only used for sampling. It's used to go through and scroll through their airways and check to actually make sure they're receiving the pressures they need to. And they were trying at all costs to avoid having to upgrade a PLC system because they didn't have the equipment to reload it or electronic copies of the file. And we have that equipment because we happen to deal with Square D a lot. So we manually re-entered the program and reloaded it for them so that they could continue operating.